Welcome everyone on this sunny or not so sunny afternoon. Before I get to today's speaker, I've got a few announcements to make. I'm Claire White, I'm an assistant professor in Andlinger Centre in Civil and Environmental Engineering. Please silence your cell phones. That was number 1 on the reminders list. Also, we have a speaker for the Andlinger Highlight Seminar series on March 7th. It's Venkat Srinivasan from Lawrence Berkeley National Lab, so I hope to see you there for that seminar. Also, after this seminar, there's a reception out in the lobby, so please join us out there. And the last reminder I have is please wait if you've got questions at the end of this seminar. Please wait until you get the handheld microphone. We're actually recording today's lecture, and so it's good to have the audio for the questions coming through as well as the response. So, today, I have the great pleasure of introducing Professor Karin Scrivener from EPFL in Switzerland. Karin graduated from the University of Cambridge, and she also got a PhD from Imperial College, where she stayed on as an academic for a number of years before she went into industry. So Karin was at 6 years, well, she was 6 years at Lafarge, which is one of the major cement companies in the world. And after which she became a professor at EPFL in Switzerland. She is a professor there, but she's also the head of the Laboratory of Construction Materials, which is working on improving the sustainability of cementitious building materials. She is founder and coordinator of NanoCem, which is a network of industry and academia for fundamental research on cementitious materials. And for those of you who have worked in Europe, you will have heard of NanoCem if you've worked in cement and concrete. She is also editor-in-chief of Cement and Concrete Research Journal, which I would say is the leading research journal on cement and concrete research. And finally, in 2014, she was made a fellow of the UK Royal Academy of Engineering. And Forrest said it's time to give a shout out also to Emily Carter, because she was just elected to the National Academy of Engineering. So we've got 2 wonderful people in the audience today, one of which is going to be speaking, which is Professor Karin Scrivener. So please welcome me in joining her to the stage.
So thank you, Emily, for this kind introduction, which is working. I hope in my lecture today I can convince you that if you don't work on concrete already, it is an interesting material to work on. It's above all a material we use. So in terms of doing research, I think we need to kind of think a little bit about why we're doing this research on concrete. You know, it's not just a theoretical subject, it is something that's very practical. And here's various reasons we can, you know, think about researching. We may want to improve the properties. We may want to develop special applications. Today, I think the main driver in the field and the thing that most people talk about is moving towards a more sustainable use of materials in the world and lower environmental impact. And unfortunately, when we come to talk about sustainability, I think the general public and the funding agencies are not really all that well informed. And we unfortunately see quite a lot of research funding which has the objective of lowering environmental impact. It's often wasted on totally unrealistic technologies, you know, because concrete is the most used material in the world. But before I talk more about that, I want to introduce this slide. Because, you know, global warming and CO2, this is a worldwide problem. CO2 doesn't stay where you produce it. And today, we have to be realistic that this is overall CO2. This is the amount we produced in OECD countries. This is the amount we produced in non-OECD countries. So even if we completely stop all our emissions in North America, Europe, this would go nowhere near solving the problem. We've really got to work on solutions that can be picked up in what we generally call developing countries. And I mean, these are overall CO2 emissions, but if we were to look at the breakdown when it comes to concrete, we would have even more of the emissions coming from non-OECD countries. So I think we've got to think about technologies not just that can be applied in developed countries like North America and Europe, but in the developing world. Now, the second thing I want to say is, you know, I mean, concrete, people have very negative views about concrete. And this is really, I think, very much unfair, because we just don't appreciate that concrete is everywhere. Concrete makes up about half of everything human beings produce. We simply couldn't do without it. And here's the comparison for three very common materials, concrete, steel, and timber. You see, concrete makes up about half what we produce every year, and in doing so, it accounts for about 8% of CO2 emissions. Now, that's actually not a bad ratio. When you look at steel here, there's about 20 times less steel produced than concrete, and it produces almost the same amount of CO2. So the amount of CO2 coming from concrete in terms of performance is extremely good. It's just because we use such a colossal amount of it that overall it produces a lot of CO2. And, you know, we come to something like timber. Well, you know, many people argue about these figures. I don't really want to argue about the figures in terms of CO2. I just want to point out to you that today we're using about 1/10 of the amount of timber compared to the amount of concrete. And we already think this is way beyond the limits of sustainability. That's to say, we're cutting down much more forests than we're replanting. So there's no way a material like timber can replace concrete. It's just physically not possible. And, you know, when I make this presentation in North America and Europe, you know, particularly countries like Sweden, they say, oh, this can't be true. We have very sustainable timber production. Yes, you do have very sustainable timber production in Sweden, but Sweden is a very small country of about 10 million people. If you go to very big parts of the world like China and India, you cannot build in timber. They do not have timber. The only choice you really have in concrete. And at lunch today, one of the students said to me, do you think there's a future for concrete? I think if you look at these figures, you realize there's no alternative. You know, we're going to be using concrete for the foreseeable future. And if we're going to be using it, what we really need to think about is how we can make it better. And, you know, this figure of 5 to 10% in perspective, because this is another thing. I made this presentation to architects in Zurich, and one guy stood up to me and he said, I think construction is causing so much CO2, we'll have to stop building in the future. And I looked at this guy. I said, are you serious? Are you telling me when you grow up, you're going to sleep on the street because we're not going to build any more houses for people? And nobody thinks it's bad that this is the same order of magnitude as the energy we spend running computers. Every time you press Google search, you are sending CO2 in the atmosphere because the servers doing that searching need a lot of cooling. So let's get it in perspective. You know, people have to live somewhere. We could say it would be better if the world population was perhaps lower. That's another debate. I don't have the capacity to do much about it, but if there are the people there, then they need houses. And concrete's probably the best way of doing it. So let's look at where this CO2 is coming from, because we need to know where this CO2 is coming from if we're going to reduce it. So cement, which accounts for 95% or so of the CO2 emissions in concrete, 40% of the CO2 is coming from the production. And this is really quite unique in terms of industrial processes, because most industrial processes, nearly all the CO2 comes from the energy in that process. So if we have alternative energy sources, like solar or wind or something, then this will largely solve the problem. In making cement, only about 40%, so even this is a cement kiln, you have a huge flame which heats the cement raw materials up to about 1450 degrees Celsius. It seems like a very energy-intensive process, but it's actually very efficient. The efficiency of a modern state-of-the-art cement kiln is at around 80% of thermodynamic limits. And those of you who study thermodynamics really know you can't really do that much better than that. And more than that, it's a very flexible process, because nowadays you can have most of that fuel coming from waste. So for example, when you're making these seats in this auditorium, you'll have lots of polymer offcuts. You can chop that up, feed it into a cement kiln, and use it as an energy source for cement. So it's a very, very flexible tool, and it's unlikely we're going to be able to make a lot of savings here. So we really have to look at this other 60%, and this comes from what we often call chemical CO2. That's to say that the first stage in the production of cement is we take limestone, which is calcium carbonate, and the calcium carbonate decomposes to give us calcium oxide and CO2. And that accounts for 60% of the emissions. Now, if we're going to change that, the inevitable consequence is we're going to change the chemistry. And if we change the chemistry, then the whole way it reacts and performs is going to change, and that's why we need research to find out what these differences these things make. Now, the demand, you know, we're not facing a static situation. We're facing a situation where the demand is going up, and it's going up fast. These are the projections out to 2050. But if we look what's already happened in China, in the last 10 years or so, the production, you know, China has invested in its infrastructure. It's built housing. It's built high-speed rail links. This all has used concrete. And today, China is producing more cement than was produced in the whole world 10 years ago. I think Bill Gates came up with the figure that in the last 3 years, China has made more concrete than they did in the USA in the whole of the 20th century. So it's colossal. And things are slowing down in China now. We read about that every day. But, you know, what's going to happen in India? Today in India, the consumption of concrete per capita is 6 times less than China. Even if India doesn't reach the level of China, even if it only goes to, say, half that amount, that's still an awful lot more cement that's going to be needed. And there's a lot of other countries in South America, Africa, the rest of Asia, that are really looking at the same development path. This is just an example from India. This is, you know, what they're aiming at now. This Delhi-Mumbai corridor, I think they've got plans to build about 80 new cities in this corridor. So before we go on to look at what can be the solutions, I think we also need to look at why this product, Portland cement, is just so good. And it is so good. I hope I can convince you of that by the end of the lecture. You know, it was invented nearly 200 years ago, so we think it's kind of, you know, old hat. But by a coincidence of geology and other things, it really does work amazingly well. Now, this is the analysis of elements in the Earth's crust. So that's a pie chart. And it's something that comes from the cosmology of stars. But basically, you have these 8 elements: oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium. This makes up 98% of the Earth's crust. And you can see in this other graph here the abundance, and you can very roughly say that abundance is equivalent to cost. So you're talking, you know, as we go down here to these rare metals, here we see the things that really cost a lot. And here we see the things that are really cheap. So you go down to some, you know, even something like barium, it's probably got to cost 1,000 times more than something like calcium. So you can make cements out of barium salts, but this is really not going anywhere in terms of solving our construction problems. But the other thing that's interesting is that then we can really do an exhaustive analysis of all possibilities. So people often come up to me and they say, what's new? Like, you know, there's going to be something, some new miracle solution we can come up with. And what I try to tell them is, look, there isn't. We know we have looked at all materials we can imagine to make cement. Because we understand the basic idea of how cement works is this. You take this gray material, these gray grains, and you mix it up with water. And at the beginning, it looks like this. You have these gray grains floating around in water. And you can move it, you can shape it, you can form it, you can put it in a mold. And then you have this reaction between this gray material here and the water to form this new red stuff, which we call hydrates. Okay? And the magic thing about these hydrates is that they have combined the water into solid form, so that now this solid, which is red, occupies more volume than the grey stuff here. And because it occupies more volume, it starts to fill in all these spaces between the grains and link them together. And that's how you get the strength. And that's basically how concrete works. So if you're going to have something that works as a cement to make concrete, it needs to react with water. The ions need to move through the water, and they need to deposit in the space. So let's look at these different oxides in the Earth's crust. And if we take the two alkali oxides, sodium oxide, potassium oxide, basically these are two soluble. You can have very high solubilities of sodium, potassium, and water. We know that. So these may be present, and they're not necessarily doing any harm, but alone, they're not going to give you this hydrating system. If we look at iron and magnesium, on the other hand, we have the other problem that these have very low mobility in alkaline solutions. So, for example, here we see a micrograph which is just taken from a piece of concrete that was just in a building, 30 years old, and you see these bright white areas. Now, these bright white areas are where the iron is, and basically the reason they're so well defined is because they're in exactly the same place they were 30 years ago. They were in the cement grains when it went into that concrete, and the other elements, the calcium, the aluminium, this is all moved around, and this is filled in the space. So you see we now have products between these grains, but the iron has just stayed in exactly the same place. So again, it's not doing any harm, but it's not really doing any good in terms of giving us strength in the system. And it's the same story with magnesium. This is a picture of a mixture of a slag cement, blend of slag and Portland cement. And these grains here, this is the slag grains, and they've partly reacted. And where they've partly reacted, you can see they've got these dark zones. And the reason they've got these dark zones is because that's where all the magnesium is. Slag contains magnesium, and the magnesium in that slag just stays where it originally was. So it doesn't go into the space here. It doesn't bridge the spaces between the grains. It doesn't contribute to the strength development. So this means we've gone from the composition of the Earth's crust, and we basically come down to this system of just three oxides of calcium, silicon, and alumina. Okay, so it's really quite simple. This is the system of oxides we can really use to produce cements. And here, if we look at this system, calcium, alumina, silica, we see we've got the composition of Portland cements here, which are basically calcium silicates. The only other hydraulically reactive minerals we have in this system are down here, and this is basically calcium aluminate cements, and by extension, with a bit of sulfate in the system, calcium sulfoaluminate cements. Okay? So in this whole system of all the Earth's materials, these are the hydraulic minerals that are interesting. Of course, as I said, you can have barium silicates and everything like that, but that's not really serious. So the problem here is that to produce these calcium aluminates, calcium sulfoaluminates, you see now we've got considerably more alumina compared to silicon. And geologically, this is rather more rare. Generally, alumina and silica occur together in nature in roughly the same proportions. If you're going to get sources which contain much more alumina, you've already got to go materials like bauxite. Bauxites are much more localized. They are under increasing demand for aluminium production, therefore they're more expensive. So if you make cements here, they're going to be a lot more expensive. Calcium aluminate cements, for example, cost today about 5 to 6 times the price of Portland cement. Now that price differential I'm going to come back to, because it doesn't all come from the geology and the expense. It comes also from the difference in scale. But it starts with the expense. Now, the second advantage of Portland cement, so, we happen to have a cement which is formed from the most abundant materials in the world, and then it has this incredibly useful pattern of reaction. Now, why is this incredibly useful? Now, this is the heat evolution, which is a signature for the reaction. And what we see is we get a very high heat evolution to start with, then it dies away, and it stays quite low for a period of 2 to 3 hours. Now, this is very, very useful because this means you can mix the concrete, and then you can transport it, and you've got this period of a few hours where you can put it in place. And not many materials do that. I mean, the calcium aluminate, or calcium sulfoaluminate systems we looked at here, generally set much faster. And this is also robust. It means it can be used by almost anybody, almost anywhere. You can say that's also part of the problem, because here's, you know, the way that a lot of concrete is made around the world. Here are people mixing concrete basically on the sidewalk, and, you know, the control of the formulation here leaves a lot to be desired. It's not the most sustainable formulation, but this is how it's done. And we have to face that. We have to realize that this is where a lot of cement produced around the world is consumed. And if we're going to do anything about sustainability, we have to have materials that can be used in a similar way. Here's a slide where we compare Portland cement, the open time. The open time means the time you can work with it for OPC and for calcium sulfoaluminate cements. You see calcium sulfoaluminate cements a very quick setting here. You can retard it with chemical retarders. This adds to the expense and the complexity, but then you've got a large area of variation. So where do we come to after all this analysis? We've seen, you know, we've got the composition of the earth. We've got these calcium silicates, which work very well, which give us our robustness. Well, what we can do then, we can actually then mix this Portland cement with other materials. And this is what's called reducing the clinker factor, because in most of Europe, this is already done at the cement plant. In North America, they try to do it more at the concrete stage, which adds another level of complication, but we don't need to talk about that today. So what does reducing the clinker factor means? It means that basically in the past, 50 years ago or so, we had clinker, which is the stuff that comes out of a cement kiln, and we ground it with a bit of gypsum, calcium sulfate, and that gave us cement. And nowadays, we introduce increasing amounts of what we call supplementary cementitious materials, and these are things like fine limestone. This is things like fly ash that comes from burning coal to produce electricity. This is stuff like slag, which comes from blast furnaces where we reduce iron oxide to make steel. And also we can have some natural pozzolans. So we have all these family of materials which we can now interblend with the cement to reduce the amount of the Portland cement clinker. And these things which are either, you know, have no CO2 associated, like limestone, because it's not heated up, it keeps hold of its CO2. Fly ash is a waste product, slag is a waste product, etc. These are basically CO2 neutral and therefore reduce the overall CO2. And incidentally, we can see that these all have quite similar chemistries. We can see here that they all tend to have the same ratio of silica to alumina, because that's what we find mainly in the Earth's crust, coming from feldspars and then clays. And if we take the figures for Holcim, which is one of the biggest international cement companies, these are the worldwide figures for their factories, you can see over the past few decades, the average amount of clinker they have in their cement has been reduced by more than 10%, and this reduction of more than 10% is equivalent to a more than 10% reduction per ton in CO2. So that's great, but what we actually see is that this strategy for replacing cement with other things is kind of leveling off. You can see that here from the figures from Holcim. There's been very little progress in the past 5 or 6 years, and these are the worldwide figures from a lot of cement companies. And we see that at the end of the day, we're really talking about 3 products. We're talking about limestone, we're talking about slag, and we're talking about fly ash. This makes up more than 80% of the materials we blend into concrete. So why is it slowing down? I'll come back to that. It's slowing down because the amounts of these materials we have are in fairly short supply compared to the colossal amount of cement we need. So we take slag. I mean, slag is a great thing. You can mix it 70% or even 90% substitution of clinker. But the amount we have worldwide is about 5% of the amount of cement we need. And 99% of that is already being used in concrete. So all the benefit of CO2 reduction from slag, we already have. We can't go any further with that because there's no more slag available. And this situation is probably going to get worse because, as you saw at the beginning, making steel produces a lot of CO2. There's big pressure on steel makers to reduce CO2, and one way they do that is by recycling. And so there's going to be less and less slag available in proportion to the amount of cement. And fly ash, okay, there's more fly ash available, but the quality is very variable. So today we can only use about 1/3 of the fly ash produced in concrete. And perhaps we can go further with that, but generally, there's a lot of it which has really very low performance, doesn't really react any more than like putting in sand or something like that. We have lots of limestone, but the problem there is we can't go to very high substitution levels because after a certain point, the performance falls off. So basically, what can we do? We've had this successful strategy, but where can we go now? And, look at some of these things like you see in the literature. There's a lot of papers coming out about rice husk ash, but the amount is tiny, and it's seasonal. And, it's not going to get anywhere near to what we have with slag. Really, if you look at this, the only material only place we can imagine to go is up here. Well, I put it against metakaolin, which is a very pure form, but we've got an awful lot of clay, which we can calcine. And I think this is the potentially big new thing in cement because it has the potential to really give us these further savings in terms of CO2. So just to summarize that, I think really we can see that blended cements will continue to be the most viable route to lowering CO2 emissions and responding to the increasing demand. And what we need to do, we need to find these new sources of SCMs. We need to increase their reactivity. We need to prove the durability. And we need to understand it from a mechanistic point of view because, most of the approach so far has been like kind of, mix it up and see what happens. And this takes much too long. The development route is much too long. And we see many, many hyped alternatives. All around there are these different things. There's a company out in California that works on recarbonating calcium. Well, that's fine. You can recarbonate calcium, but where do you get the calcium from in the first place? There aren't many sources of calcium in the world that don't already have the CO2 attached. And the problem is these radically new materials, Portland cement is very effective because of the economies of scale. I told you about calcium aluminate cements, and I said these cost 6 times as much as Portland cement. The reason they cost 6 times as much is not just because they're made from bauxite. It's because there's so much smaller volumes, so the number of people you have to make the product, to sell the product, to provide technical assistance increases in proportion. So, that's what I've said here. That's what I've already said. Right, so what's a realistic solution? The only SCM, as I see it, potentially available in the quantities we need is calcined clay. And this is what we've started working on. It was a project that gradually built up and now really has been going full scale for about 2 years. And interestingly, our funding is not coming from the National Science Foundation. It's coming from the Swiss government agency responsible for development and cooperation. So this is like an overseas aid budget. It's quite a challenge working with these people because they're not scientists, and they don't understand it. But it also puts a big pressure on us because we actually have to try and get people to make this stuff, not just stay in our laboratories and do nice things. So we've called this material LC3. We started out calling it low carbon cement, and then we realized everybody called their solution low carbon cement, and we said, let's not make a value judgment, let's just say what's in the tin. It contains limestone, calcined clay, and it's a cement. So we called it LC3. Now, where this gets interesting is if you look at where we have clays. And clays are one of the most abundant minerals on Earth. And the clays we really want are the clays which contain kaolin. And these clays we generally find in this region of the world. So certainly where we have yellow regions, certainly where we have this kind of lime green color, but also in India, we've found very, very abundant deposits in this region of Rajasthan, which is not showing, but generally in all this region. And what's really now exciting is that these regions coincide with exactly their countries where they want more cement. So we have a really good coincidence between the availability of the material and where they want to use it, and often it's sitting around like this. This is a picture from India. This is a quarry where they're extracting clay to make plates, but a lot of the stuff in that quarry is not sufficiently high grade to make pottery, so they just leave it in these heaps. And we've taken material from these heaps and we've produced this material. I'll show you the results in a minute. So, you know, often you don't even need to open up new quarries. You can just go and collect it and take it away. It's a waste in the same way that slag and fly ash are waste. Now, here's what is really the secret, that this is a Portland cement, which is clinker and gypsum. We've for a long time known about these kind of pozzolanic materials where we typically have 70% clinker and about 30% pozzolan. Can be calcined clay, can be fly ash, can be whatever. And where we sort of was the kind of breakthrough was putting this together with the idea of limestone, because it was shown that limestone actually reacts with alumina. So you've got a little bit of alumina in your clinker, but you've got a lot more in your calcined clay. If you put this together, you can go to now 50% substitution. And if you look at these typical strength results here, you can see as early as 7 days, these materials, which contain less clinker, less CO2, are giving us higher strengths. So it starts to get really exciting. And this is, of course, we've done the analysis behind it. We know what's going on in terms of chemical reactions. We have, sorry, this is in cement chemist notation, where A is alumina oxide, S is silica, etc. We have alumina and silica coming from the clay. We know they can react with calcium hydroxide, which is produced by the clinker, to produce CSH and other alumina phases. We know that limestone can react with alumina. Well, we put the two together, and we can get a lot of this phase, which we call calcium monocarboaluminate. And this is a hydrate like any other hydrate. It fills space. It bridges the gaps between those grains. Now, it does depend somewhat on the quality of your clay. So you can see here we've got different clays containing different amounts of kaolin. And generally, the more kaolin they contain, the better they will perform. But if we look at a lot of clays, and we've now tested about 20 clays in this benchmark system, we can see that we just get a very strong correlation with just one parameter. And this is very interesting, because when we first started out, people said to us, oh, there's all different clay mineralogies around the world. How are you going to work out what works and what doesn't work? Well, what we can show is that it really only depends in the first approximation on just one parameter. And this parameter of kaolinite content you can measure extremely easy just by looking at the weight loss step around 500 degrees. And these little dotted lines, this show the reference strength of the pure Portland cement. So you can see that even for kaolin contents as low as 40%, you can match that reference strength of your Portland cement even as young as 7 days. So, you know, we know how to assess the clay quality. We know what are the important parameters. So that's great. We know the chemistry. We've analyzed the phases. We have all sorts of nice micrographs on that. But the point is it just a nice idea in the lab? Well, that's where things got interesting, because I started this project in collaboration with a professor in Cuba who is the most brilliant optimist I've ever met in my life. This guy he just overcomes all obstacles. And he said, we're going to do this. We're going to produce this in Cuba. And this is the picture of the production. And when I saw this, I felt like crying. Because I felt like we've been 4 years on this project. And I mean, this was really awful. You know, look at this pile here. There's all these black lumps in it. And this is an old Russian kiln. And I mean, it was just a nightmare scenario. They started making this stuff. And the kiln started melting. They had to shut it down. I mean, you know, nightmare. I said, this is never going to work. But Fernando, who's an optimist, said, we'll do it. And the point is, it worked. We can make concrete. And here he is. Sorry, here's Fernando back here, standing in the concrete yard. I mean, you just do not realize what a miracle this is, because you produce it almost any old how. You take it to totally unskilled workers in a precast plant. You say, use this new material, and it works. I mean, my God, that's amazing. Absolutely amazing. I really promise you this is amazing. And, you know, we can build houses out of it. We have it being tested for durability. This is the durability site off the Cuban coast. Perhaps when the US government finally ceases the embargo, you can go and visit there, and it's a very nice place. There's a nice resort just up the beach from there. And so we went back to this agency, for, you know, SDC, and we said, well, this is great. What should we do next? And they said, well, you know, Cuba, it's this very small country. Their CO2 emissions per person are almost about the lowest in the world. So what? You can produce this cement in Cuba. It won't make any difference in terms of CO2. If you want to make a difference, you've got to go to India. Right. So we went to India. Luckily, we had the connections. We had ex-PhD, our former PhD students who were the people, again, the heroes who put everything together. This shows the first production we made. And it's, again, a real horror story. Okay, it's not quite a horror story as this, but these pallets here, it's not a very good way to do it. The calcination is not complete. It was about 50% complete in this case. But we took it to people making roof tiles. This is totally unskilled workers, illiterate workers, making these roof tiles. Give them the stuff in the bag, exactly the same as the material they're using. They can make these roof tiles. They can demold them in exactly the same way they're doing them. And here's the strength results. You see, this is the material they were using, which is the fly ash blend. And these were all the materials we made in our concrete, in our trial production. You see they're a little bit stronger, but the point is they're the same. And they made all these components, and they built a house. So we now have a nice house as a demonstration. And interestingly, we made the calculation, in building this house, we could save 7 tons of CO2 compared to existing solutions. This is even compared to using fly ash blends, okay? So this is over and above what you had before. So that's basically the story. That's where I think, you know, a lot of our efforts are going in the future years, but there's an awful lot to do. And, you know, I think there's so much, you know, I mean, always people want proof. We need to look at durability. We need to look at shrinkage, creep, and cracking. All our results are positive so far, but, you know, we are working in a world where cements need to be standardized. People don't like change. It needs scientific work behind it, but I think it can be done, and hopefully other people will see the interest of these materials and start doing some research themselves, which can build the critical mass. Now, what can be the impact of this? And I think this is where you know, you really see what can be done. Now, these figures here, they're a bit difficult to explain. This was a study done by the International Energy Agency for what's called the Cement Sustainability Initiative of the World Business Council for Sustainable Development. Sorry about all these initials. And what they said, okay, we think that in order to meet this 2 degree global warming target, the amount of, the global amount, not the amount per ton, the amount we need to cut from cement production is about 18%. And these graphs were done in a low demand, high demand scenario. And they said, let's look at all the technologies we can imagine. We know we can continue to use substitute fuels. So this is well adopted in Europe and North America, not so much in other countries. If we continue to use substitute fuels, we can save this blue amount. If we continue with moves on energy efficiency, that's to say state-of-the-art plants are very energy efficient, but a large proportion of cement plants around the world are old and need replacing. If we do that, we can save this red part. And if we continue with the strategy of clinker substitutes, we can get this green part. And the reason this green part is so small is because if we look at the forecast supplies of things like slag and fly ash, we estimate that by 2050, we're only going to have 1.2 billion tons of supplementary cementitious materials. Now, if we could, and then they said, okay, the rest has to come from carbon capture and storage. Now, you know, they've done full-scale pilot studies of carbon capture and storage, and it's basically going to increase the cement price 2 to 3 times. Okay? In North America, you may say to people, you've got to pay 2 to 3 times the price for your cement in your buildings. It could be done. People won't like it, but they can afford it. In India, in Africa, I don't think it's going to happen. But if you can increase the amount of supplementary cementitious material from 1.2 to something which is very reasonable, given that geology of clays I showed you earlier, to 1.8, then you can grow that green portion from that to that. And you can almost entirely do away with any need for carbon capture and storage. And you can do that cheaper. You can do that at a lower cost. So it's a self-driving phenomenon. Once people kind of get used to this idea, they'll do it because they can save money. And you can save potentially about 300 million tons of CO2 a year, which, just put in context, is like wiping out the whole CO2 emissions of a country like France. So that's not bad. Some people say this is nothing. But I think if you have one single technology that can save about 1% of world CO2, that's not too bad. Yeah, we should go for that. That's just a slide to show you the cost of carbon capture and storage. So I'm nearly finished. Sorry, I've probably been going on way too long. But I think, you know, the points I want to make is that really if we want to impact the sustainability of concrete, we must have new solutions that can also be used in developing countries. It's no good having something that can just be used in a very sophisticated precast plant in Europe or North America. This is not going to have a very significant impact. The solutions must be practical. They've got to be usable in the field by unskilled workers. And I think, therefore, that calcined clays and this, what we call the LC3 technology, have great potential to contribute in this regard. The thing that's really amazing is that they are so robust. This is partly because you've still got the Portland clinker there. This means that the pattern of reaction with this time to place the materials in the mold is still there. And we've done quite detailed environmental assessments, and you can typically lower CO2 emissions, certainly by 30% compared to pure Portland cement, but even by 10 or 20% compared to existing pozzolanic cements. This is important for countries like India. In India, they only have enough proved limestone reserves in places that can be, where quarries can be opened, probably to open cement plants for the next 20 years. You know, that's not very long. And so if we can potentially extend the limestone reserves, and we can do that because we can produce about twice as much cement from the same quantity of limestone. And we also have reduced costs and reduced capital investment for increased capacity. So that's where we are. On top of that, we're also kind of not only looking at calcined clays, but looking at all kind of options for practical development of new solutions to concrete. This is our task force. Claire may recognize this person here. You know, we're trying to put together all these different scenarios and quantify them. So that's just, this will come out in Cemented Concrete Research in autumn 2016. But I think with that, I'm going to stop. And if you have any questions, I'll try to answer them. Please go to our website if you want more information. There's lots of nice videos there. Particularly, there's a nice video my students made called Minute LC3. So if you type Minute LC3 in YouTube, you'll find a nice little cartoon there about this technology. Okay, thank you very much.
Thank you so much. I feel, Claire, you'll be happy. You know, I feel like an expert in concrete like never before. But I'm still confused on one thing. Maybe just sort of to start off with something to clarify for me. As I understand it, once you make the concrete, right, the chemical reaction produces the CO2. But then over the lifespan, if we've just produced all this concrete, there's still this calcium, like the calcium still absorbs CO2 somehow?
Yeah. So, okay, it can all go back. And on geological timescales, it will go back. It will all reabsorb that CO2 again. The problem is that you've got this real time delay between the speed at which you're putting it out and the speed at which you're reabsorbing it. So to reabsorb it, you're talking about hundreds of years. So, you know, people have done calculations on that. I think it's a little bit delicate, because the other thing is if you totally absorb all the CO2 black, it won't protect the reinforcing steel anymore. Now, that may not be a problem in other things. I mean, I was amazed to find out through this task group we're working with that only about 25% of cement worldwide is actually used with reinforcing steel. But, you know, I think we shouldn't count on that. Even though it's a kind of, it's a bonus, I think we shouldn't count on it. It's like saying all the steel is going to rust and turn back to oxide again. You know, it is, but we don't really want that to happen.
So it seems like the tests that you've done on these new materials is mostly mechanical compressive tests, right? For compressive strength. But you are doing other tests like having it sit in seawater.
Results,
So, I mean, I'm just wondering, and I think this is great, and the question is, you know, is it the case, it probably is the case, that the building codes are lax enough in India and other places that you could imagine, whether or not it's a good idea or not, to actually start using these experimental composite concretes, you know, to build buildings, just like you did the pilot house. What are your thoughts about that?
Well, okay, this is a long process, and this is what we're really engaged in. Actually, in India, the codes are way worse than in North America.
Oh, okay.
In North America, you actually have a more flexible standard under which you could produce this stuff, you know, quite quickly. But, you know, with all these new kind of materials, you have to go one step at a time. And usually the first step is this. This is what we call concrete products. You see, this is no reinforcing steel, because the main durability issue with concrete is actually the steel. The steel corrodes. So you've got a lot of applications like this where you can use the concrete without the steel. And also, these kind of products are usually tested on the end product. So you can put in any rubbish you like, even today in all countries of the world, North America, Europe, India, anywhere. You can make products like this. You don't have to meet any, you can use any kind of cement you like. What you have to do is be able to test the material at the end of the day. Okay.
All that matters is mechanical strength? For those
because a building like that is not really under very aggressive conditions. There's no seawater there. Okay? Carbonation can occur, but we've got no steel in there, so we're not worried about that.
What about acid rain?
Acid rain's not that bad now. I mean, generally most power stations have started to clear up. Maybe in China you've got a bit of an issue. But, I mean, I've done work on acid rain on roof tiles. I mean, you know, we did a lot of work in the past on roof tiles like this. It's not that bad. I mean, you can have these under very acid rain conditions for 40, 50 years. They won't fall apart. They may look a bit discolored on the surface, but they won't fall apart. So this is the first entry step. And then, of course, when you're looking at reinforced concrete, you know, when you're looking at concrete like this, then it's got reinforcing steel in. You have to be a lot more careful. So this is why you do durability studies like in seawater like this. Our first results are extremely good. They actually show this is probably going to be a real driver, certainly in Cuba, because they're really developing the tourist infrastructure. A lot of it's at the edge of the sea. At the minute, they've got terrible durability problems. And, you know, our results from this site are looking extremely encouraging. But I didn't have time to put all that in because then I'd been speaking for 2 hours rather than 1 hour, and I think most people have fallen asleep by then. But it looks very, very good. Yeah. And just one more point, though, but I think it's very important. I think the important thing about this is at the end of the day, the phases we've got, the chemistry, is all chemistry of things we know. So we've got known chemistry, and we need to know about the pore structure, but we study the pore structure, and we know how that varies. So we're not like shooting in the dark with a new material. Sorry, you had a question down here.
No problem. Thank you for your talk. Did you look at vapor permeability with respect to subterranean applications?
We didn't look at that specifically, but I expect that to be another kind of advantage. We see that these have generally got lower permeability, so they'll be more watertight. But in its first approximation, the vapor transport is going to be pretty much the same because you've got the same mineralogy and you've got a similar pore structure.
How these new cements, like steel reinforcing and in particular pre-stressing.
Yeah. Sorry, what was the beginning of the question?
The question of reinforcing with steel and pre-stressing, compressed concrete.
Yeah. What about it? Oh, you can use it exactly the same.
It's identical with the bottom.
Yeah. From those points of view, I mean, you know, in those kind of applications, what people are really concerned about is do they protect the steel over time? And there you've got two issues. You've got chloride, where things are a lot better generally. You've got carbonation, which can be a negative, but it's like the same for all these materials on the market, like slag cements. But generally, if we look at equivalent strength, we see pretty much equivalent performance in terms of carbonation.
Thank you. The kaolinite that you're using, it takes several thousands of years to produce from weathering reactions.
Yeah.
Whereas limestone is there, it's very easy to get. So if you start using kaolinite for this, you're actually going to use all the precious resources that we have.
Well, I think it's pretty much the same between limestone and clays. I mean, the amount of limestone we've got is also being depleted. In fact, I mean...
a lot more limestone than kaolinite in the Earth's surface system.
I think it varies locally. I mean, what we know in India is we've got huge amounts of stuff like this. And they've actually got more clay deposits in India than they have limestone deposits. In India, the big problem is limestone.
You start using the waste materials, that's fine, like the one that you showed, but slowly people start actually digging and actually using the precious materials.
But, I mean, again, we use clay to produce cement at any rate. At the end of the day, we have to say, if you're going to have a building here, it's got to come out of the ground. What's the most efficient way to do it? Now, I made some calculations. If you use compressed earth, it's not a very strong material. You actually have to use about 3 times as much as if you produce concrete. Okay, so concrete is actually, again, a very efficient way of producing a house. Now, you're right. Eventually, we're going to take stuff out of the earth. But it's a question of choices. If you do it with steel, you're taking more material out. If you do it with timber, we just simply don't have enough. So the only solution you've got to say is we've got to reduce the world population. Now, I maybe would agree with you there, but I don't feel that's something I can solve with my scientific
But the issue is with limestone, we have hundreds of meters thick of limestone deposits, whereas we have few meters thick kaolinite deposits. So that's a big difference there.
As I say, our first prospects have shown that we have, in India specifically, where we've done the studies, we have a lot more clay reserves than we do limestone reserves. So, I mean, you may be right, but in the particular problem they're facing in India, it's going to be easier to do this than they just don't have limestone quarries.
This may be a totally ignorant question that doesn't make any sense, but is it possible to think about, because since we're talking about, whether we have enough of a resource, of recycling concrete?
Oh, that's a very good question. Well,
in a way that doesn't cost a tremendous amount of energy to do it. Right?
No, I mean, this is right at the beginning. I had a slide about comparative energy of CO2. This is a huge issue. And the problem is you can recycle concrete, but actually in recycling it, you actually produce even more CO2. So
the challenge is how to do it without doing that.
Yeah. So, I mean, because you have to transport it, because you have to crush it, this all produces extra CO2. Now, of course, you may have good reason to do this because of lack of resources. And this is a debate that's going on, particularly in terms of aggregates. Many parts of the world, they're already doing that. So the technology exists there, and when in fact, the cement is not the problem. The aggregates are the problem, because cement is about 1/10 of concrete. So that's also why it's quite efficient, because, okay, you dig the materials out to make the cement, but then the final product, concrete, most of it is just rocks. And you can use any old rocks of any composition. But even in many countries, aggregates are becoming an issue, and then the people are being obliged to recycle, which can be done. It produces more CO2, which is a bit of a problem, but it can be done if you're lacking resources.
In the context of the resource availability, can you just go back to the slide then that you had the list of available slag and fly ash?
Yeah.
I can't remember. I think you had like a rough arrow of what the metakaolin.
Well, I mean, that was just that's pretty much just a schematic. I mean, I put it like that because it's very widely available. I think what's more realistic is the one I showed at the end when I said we could go from 1.2 billion to 1.6 billion. I think that's a very realistic calculation. But going back to this resource problem, I think it's like I said about we use computers and we don't think about the fact they generate CO2. Do you know how much resources need to be extracted from the earth to make a gold ring like that? 20 tons. And we don't think anything about depleting resources when we go and buy jewelry, do we? But all of a sudden, when we're building a house and we have the most efficient materials, then we start worrying about resources. So, I think we're living on this planet and we're depleting all our resources. We have to think about making choices, and that's a debate that needs to take place. But I can't solve all that problem. I mean, I'm just saying, as a cement chemist, this is a problem where I think we can start to provide some answers. But there are much more difficult problems. I don't know how we're going to solve them. I don't pretend to.
If you could replace the other 50%, do you think there is a way? And you're developing the first 50%.
I think you get into a law of diminishing returns, because, as I said, you take something like compressed earth, and a lot of people say, well, earth construction is wonderful. And this is really a problem. I mean, in parts of India, they've had to ban earth construction because people were just using the soil, in the fields. At least we're not doing that. And you have to use 3 or 4 times as much just because the strength is lower. Again, this is where cement provides the most efficient solution. Okay? So it's the most efficient. You won't do better by substituting it. Maybe we've got to, as I say, cut down the number of people.
Not maybe.
I wonder if you investigated the possibility of using naturally produced clinker. There are, when there's underground fires of coal that actually produce the clinker, and I don't know if there's enough to be used.
This is like a kind of anecdotal thing. There are these natural cements around the world, but I mean, these are tiny amounts, absolutely minuscule amounts compared to what we need. I mean, there's a well-known mountain on the sort of hill on the border between Israel and Jordan that a lot of people have studied. And the reason they've studied it is because people who are interested in nuclear waste management, think these natural analogs are very interesting because they have the kind of timescales of thousands of years they're talking about. But, I mean, this is not available on the kind of scales you need. And in fact, it's also no different. I mean, mineralogic is no different. I mean, in France, they have a distinction between what they call natural cements and synthetic cements. And it's really just a question of definition. It's just some geological deposits, you happen to have limestone and clays mixed together in the proportions you use to make cement. So you just dig it out, and you don't have to do any mixing. You put it in the cement kiln, and you produce cement. Usually when you produce cement, you have a limestone source here, and you have a clay source here, and you mix them together, and you fire them. But mineralogically, it's exactly the same thing. But they just use these words natural and synthetic. But to me, it's a total artifice.
Huge deposits of clinker.
Yeah, but they're not accessible. They're not accessible. They seem huge to you, but look at the amounts we're talking about. We're talking about billions and billions of tons, and these are generally underground. So you've got to go into sort of deep mine extraction, which is not as efficient as the way we get limestone and clay in most places today.
I think I get the final question.
Yeah, okay.
So I'm going to turn a little bit cement chemistry and ask a cement chemistry question. Do you think you're at 50% clinker when you put in the limestone and the metakaolin? Do you think it's possible to reduce that further, potentially by bumping up the pH with some kind of alkali?
Well, we've done a lot of work on alkali in that logic, and the problem is it actually doesn't work. You can get a very short-term gain, but the long-term performance tends to be down, okay? And we just finished the thesis, which is published, and we think we work out why, because, in fact, the alkali destabilizes in the long run a lot of the phases like ettringite, which contribute to the strength development. So you may get a higher strength in one day, but at 28 days it will tend to be down.
Great. And with that, please join me in thanking Professor Scrivener again for her talk.